Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on February 25th, 2026, just yesterday. It tackles the frequent training collapse in agentic reinforcement learning, proposing a new optimization method called SAMPO that achieves an average 25% improvement over the GRPO baseline. The paper is titled ARLArena, a unified framework for stable agentic reinforcement learning. And as we'll see later, the implications for stabilizing large language model agents are quite significant. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 provides a roadmap of the methodology. It starts on the left with Part 1, establishing a standardized test bed using behavior cloning and format penalties for reproducibility. On the right, Part 2 decomposes the policy gradient landscape into 4 dimensions to isolate design choices like important sampling clipping. The center section, Part 3, highlights key findings, notably that tolerant clipping triggers model collapse. Finally, Part 4 at the bottom synthesizes these insights into SAMPO, the unified algorithm built to resolve these stability issues. So Figure 2 presents the concrete training results on the ALFWorld and Sokoban benchmarks. On the left for ALFWorld, and on the right for Sokoban, the vertical axis tracks the success rate over training steps. You can clearly see the proposed method, SAMPO, represented by the solid, dark blue line, climbing steadily to the top in both charts. In contrast, many baseline methods, shown in dashed or lighter lines, suffer from significant instability, often improving initially, but then collapsing downward. This visual evidence confirms that SAMPO effectively stabilizes the learning process, where other methods fail. Alright, Table 1 details the specific algorithms examined in this study. It decomposes methods like GRPO and SAPO into 4 core dimensions: the loss objective, advantage calculation, important sampling clipping, and dynamic sampling. The columns on the right highlight how each algorithm clips updates differently depending on whether the advantage is positive or negative. By isolating components like the sequence level weighting in GSPO or the step-based advantage in GIGPO, the authors can pinpoint which design choices stabilize training and which lead to the collapse we saw in Figure 2. Table 3 now quantifies the performance across 4 agentic tasks using these design dimensions. The top row sets the baseline with GRPO. In the important sampling section, the red values for SAPO and CISPO show that tolerant clipping actually harms performance, whereas GSPO improves it. The real standout is the bottom row, where the proposed method, SAMPO, achieves the highest scores. It boosts the ALFWorld success rate to nearly 93% and delivers a 25% average improvement over the baseline. Well, Figure 3 reveals the volatile training dynamics behind those scores. In the leftmost panel, the dashed red and purple lines for SAPO and CISPO rise quickly, indicating rapid initial learning. However, they soon suffer a catastrophic collapse. The middle charts explain this failure. Massive spikes in KL divergence, which tracks how far the model drifts from its original behavior, show the optimization becoming unstable. This instability eventually breaks the output structure, visible as a sharp drop in the valid format ratio on the far right. So, investigating that collapse further, Figure 4 digs into the token-level statistics to find the root cause. In Panel A on the top left, looking at standard SAPO, the yellow line tracks the rate of tokens falling outside the clipping range. It spikes dramatically around step 130, right when the model collapses. The dark blue bars show this spike is driven almost entirely by the lower portion, which corresponds to negative advantage sequences. Below that, the stream graph in Panel C turns chaotic at the same point, dominated by those negative advantage regions. By contrast, Panels B and D on the right show the sequence-masked version, SAPOSM, where the out-of-bounds rate stays low, and training remains stable. Wrapping up, 2 takeaways stand out. Stability in agentic reinforcement learning demands strict sequence-level control, and tolerant clipping strategies often trigger collapse. By solving these issues with SAMPO, the authors provide a reproducible foundation for training agents on much harder, longer tasks. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.